Alright, in these examples we're going to use the logistic growth model that we just looked at, the differential equation and the function value that we developed. So just a refresher, we know that we have this logistic growth model, dp dt is equal to k times p times the quantity 1 minus p over n. So whenever we're looking for a differential equation, we're going to start here. And the formula, the function formula for population, we're going to use this model that we just developed for when we're trying to find a formula for population. It wouldn't be a terrible idea for you to know these two formulas because the derivation of the second one is difficult. You can kind of logic your way to the first one if you really think hard, but it might be better for us to know these formulas so that we can apply them when we need them. Alright, so first, write a differential equation for the population. Okay, so the differential equation is going to be dp dt equals kp, so 0.04p, times the quantity 1 minus p over n, 1 minus p over the carrying capacity. And so there's our differential equation for this population. And then to find a formula for the population in terms of p, we're going to, again, go back to this formula up here, but in this case we're going to need to use the initial population to find the value of a when it's all said and done. So I set up this formula. Population is equal to the carrying capacity over 1 plus a e to the negative 0.04t. Okay, and now all I need to do is solve for the a value. I'm going to use the initial condition to do that. So I'm going to put 20 in for population, and 0 in for t, and so this turns into 20 equals 200 over the quantity 1 plus a. Solving that, we get 1 plus a is equal to 10, so a is equal to 9. And now we can write our final model for the population in terms of p. P is going to be equal to 200 over the quantity 1 plus 9 e to the negative 0.04t. And that's going to be our population model for this particular situation. Alright, let's look at the next example. A population of wild horses is represented by the logistic differential equation dp dt equals 0.08p minus 0.00004p squared, where t is measured in years. Find the k value and the carrying capacity for this population. So realize that what we want to do is we want to distill this equation into the form dp dt equals kp times the quantity 1 minus p over n. And so kind of distributing this through, realize that what we've got here is dp dt equals kp minus kp squared over n. And using that, we know that k has to be equal to 0.08, and we know that k over n has to be equal to 0.00004. So since we know the k value, we're going to put that in here to find m. And we get that m is equal to 0.08 divided by 0.00004. I'm going to go ahead and calculate what that value is. So we got 0.08 divided by 0.00004. And so m is going to be equal to 2,000. Now in part B, we're told that the initial population is 10 horses, and we're supposed to find a formula for the population in terms of t. Well, now from part A, we know the k value and we know the m value. We're going to go ahead and substitute those into our population formula. Oops. Go ahead and substitute those into our population formula. So we get population is equal to 2,000 over 1 plus a e to the negative 0.08 t. And now all we need to do is use the initial population to solve for a. So the population at time 0 is 10. 10 is equal to 2,000 over 1 plus a. So a has to be equal to 199. And so our formula is going to be p equals 2,000 over 1 plus 199 e to the negative 0.08 t. And that's going to be our formula. And now in part C, we want to know how long it's going to take for the population to reach 350. So all we're going to do is put 350 in here for population. So 350 is equal to 2,000 times 1 plus 199 e to the negative 0.08 t. And now we just need to solve this for t. We get 1 plus 199 e to the negative 0.08 t is equal to 2,000 over 350. Subtracting 1 from both sides, we get 199 e to the negative 0.08 t is equal to 1650 over 350. All I did was subtract 350 over 350. Then we divide by 199. Don't feel like calculating that yet, so I'm just going to write 350 times 199 in my denominator here. And then we take the natural log of both sides. And divide both sides by negative 0.08. Now I'm going to go ahead and calculate that. So we've got the natural log of 1650 over 350 times 199. There's the denominator, there's the natural log, divide by negative 0.08. And we get that t is equal to 46.784.